Okay, our goal is to get through section 10.8 today and to be done with that. That's why I'm just going to start in there. Microphone is working, I think. And I'm sitting real close to it and away from you guys. So, don't take it personally. It's because I can. What kind of table did we make on the page before? Good. So we're going to be plugging in thetas, right? To an R equation, so we now have R equals F of theta. We're going to be plugging in theta values. What should we remember about the theta values?
They were in radians?
Yeah, you could technically do degrees too. What do I mean by strategically? Yeah, let's go by increasing angles, probably starting at 0. Depending on the function, once you guys get the hang of polar curves, and once you kind of figure out what the different shapes are, and I showed them to you at the end of yesterday, right? They were down here. We have, these are the basic polar curves. You have the different limaçons. Some of them double back in on each other. Can anybody figure out, and we did one of these, was it yesterday or the day before? It was yesterday. When a limaçon doubles back in on itself, what kind of radii comprise that portion? What's going on? Do you remember? You were going, you were going, going, you were going, and suddenly the radii turned negative. So it's like a positive radius, if you think about it, going out, a positive going out towards angles. And all of a sudden in the second quadrant, maybe even at pi, it goes backwards. It goes backwards, backwards, backwards. It's kind of hard to see here. It goes backwards, 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 backwards. And all of a sudden in the fourth quadrant, it goes ahead and starts going forwards again. So the way you get an inner loop is when you have some negative radii. This one would just go to a 0 and then go right back out. It wouldn't actually go negative to get the loop. This one goes in just a little bit, but it doesn't actually go to 0. This one just goes flat. These are all different types of limaçons, and they always happen every time you have an equation of the form a plus b sine or cosine. Could be plus or minus. You have your different, they're called rose curves. I know they don't look like roses, but we can just think flowers, right? And the different flower ones, you have no plus or minus on them. You just have functions with cosine or sine, maybe a number in front with different thetas, like a 2 theta or a 4 theta or a 6 or a 5 theta. Depending on whether the petals are odd or even, if the petals are even, if n is even, then you're going to have twice as many. So for this one, how many petals are there? Let's see, 1, 2, 3, 4, 5, 6, 7, 8. On that one, the specific function would have been cosine of 4n. There's a 4 in there, so there are twice as many petals. But for this one would have been just cosine of 3n. So when you have an odd number, oh sorry, I said 3n, I meant 3 theta. When there's an odd number, there's the exact same number of petals. When it's an even number, there's twice as many petals. That's something kind of funny that happens with rose curves. Let's see, this would be sine of 5n. And this would be sine of, I did n again, theta. This would be sine of 2 theta, because there are 4 petals. Anyway, that's something to know about rose curves. They look like no plus or minus, just sines, cosines. And then you have every now and then some special ones where you could have a circle from just cosine theta, like we saw yesterday, or just sine theta, maybe a number in front. You can have what's called a lemniscate that looks kind of like an infinity sign, right? Or a slanted infinity sign. And that's when you have cosine or sine of 2 theta, but with a little squared in front. R is being squared, that's what's different. Okay. Why I'm showing you all of those right now, even though we're talking about tables, and we're not talking about memorizing polar curves, is because choosing theta strategically. Sometimes once you get the hang of polar curves, sometimes you can choose theta that would give nice values. What I mean by that was yesterday. You guys remember yesterday when we went ahead and were solving? Some of the values were not so nice. Like, why was pi over 3 not a nice angle when we were doing this? Do you remember what happened? Yeah, I got square root of 3 over 2. That's not nice. Like, what is that? Well, we finally figured out that square root of 3 over 2 is like 0.8. So maybe you could do 0.8 in your head. That one's not very nice. So if we had left out those points at pi over 3, if we had taken away this one, and if we had taken away that one question, could you guys have connected it without even worrying about the yucky root 3 over 2? Yeah, maybe. Maybe you guys could have connected without even worrying about the yucky decimals and going to our calculator. So maybe we could choose our values a little bit strategically and say, let's forget the yucky root 2 over 2s and root 3 over 2s if we can, and let's just stick with the zeros, the 1/2s, and the 1s all around in different quadrants. Okay, and then down below, once you've tried to graph a polar curve, there are a couple ways you can confirm that you're right. Of course, you can confirm with the charts of polar curves that I just showed you. You could try it with the table and then compare with the chart and say, hey, did I graph it right based on what the equation looked like? But then the other way, use your graphing calculator, right? And just like we saw before we even started chapter 10b, remember in polar, a lot of things can go wrong. So with your grapher, we're just going to say really quickly, watch out for polar dangers. You guys remember those crazy stars and stuff that we were getting that didn't look like any of those curves we just saw? Oh, not polar curves, polar dangers. So watch out for your window, your theta min, and theta max. Remember, if you're in degrees or radians, those are very different as to what you want them to be. And watch out for your theta step. And that's besides thinking about your x's and your y's as far as zooming in and zooming out. The theta mins and theta maxes can make all sorts of trouble. So yes, your grapher is good, but you gotta know how to use them, or else you're gonna get some funny pictures which are cool, but might not be at all the right one that you're looking for. But long story short, to graph with a table, what are you gonna have to know? You need to know your unit circle, like you guys should know. All right, there are some other clues with graphing. I'm not going to necessarily make you guys memorize these. I think last year I kind of did. I was a little bit harder on this as far as what they should know, shouldn't know. I don't think I'm going to make you guys know them this year, so I'll take them off the test if they're on there. I want you to recognize them, but you don't necessarily need to memorize. Even though the homework's going to have you try to find the symmetry, I'm more interested if you guys can tell from the equation and from its graph what kind of symmetry it has. So, since we're talking about polar curves, if you see a function going one way in the first quadrant and copying that in the second quadrant for every point. For instance, I could take that one we graphed yesterday. That did like this. Do you guys see how whatever is on the right was copied on the left? Right? We're going to say that has, we could call it y-axis symmetry, but since we're in polar curves, we're not going to call that the y-axis. We're going to call that the theta equals pi over 2. So instead of calling it y-axis symmetry, that's rectangular. In polar, we're going to say it has pi over 2 symmetry. Does that make sense? Pi over 2 is that line, that vertical line. So the wording just changes a little bit. So if you have something on the right and on the left, you're going to have pi over 2 symmetry. Just a quick hint, pi over 2 symmetry what curve in the first and second quadrant, what trig function is the same in the first and second quadrant? A function that commonly has pi over 2 symmetry is anything with sine. Because if you think about the sine curve, the first quadrant and the second quadrant go through the same values. This is 0 to pi over 2, that's pi over 2 to pi. Or you can also think about it if you don't want to think about sine, sinusoid. You could also think that all the sine values in the first and second quadrant are positive, so they're the same types of values. Sine does not get negative in the second quadrant. And that's what's going on down here at the bottom. The book would say the clues to be able to figure this out is to replace r and theta with negative r and negative theta. You could also replace it with the other, but negative r and negative theta usually works. And so it's kind of like when we would figure out even odd symmetry, we would plug in a negative x and see what happens. We can kind of do the same here with pi over 2 for y-axis symmetry. For x-axis symmetry, whatever is at the top is copied at the bottom. That's kind of similar to the one that we saw yesterday, that was that Loomis one. You guys notice whatever was in the first quadrant gets copied in the fourth quadrant. Normally we would say that's x-axis symmetry, but instead of calling it the x-axis, we call it the polar axis. Positive x-axis is also known as the polar axis, so the wording, once again, is just a little bit different. And what happens this time is whether theta is positive or theta is negative, the r stays the same. Yes, there is another way of doing it. Guys, once again, this is not something to memorize, it's something more. I just want you to be able to recognize it in a graph. Does that make sense? Okay, good. And a function that normally in the first and fourth quadrant is the same as cosine. Think about the cosine curve, whatever's in the first quadrant, there's the second quadrant, there's the third quadrant. Is the same in the fourth quadrant. First quadrant and the fourth quadrant are the same. You can also think that cosine is positive in the first quadrant and in the fourth quadrant. Functions only dependent on cosine are going to have this symmetry. Other functions sometimes too, but usually the cosine ones have polar axes. And then we have what we would call origin symmetry in rectangular mode. In rectangular mode, in polar mode, we don't call the origin the origin. What do we call the origin? Exactly. And that's why we say it has symmetry with respect to the pole. So symmetry with respect to pi over 2 is the first one. Symmetry with respect to the polar axis is the second one. And symmetry with respect to the pole is the last one. This one's kind of the weird one in the fact that whether r is positive or r is negative, theta is the same. I'm trying to think of a graph that would have this symmetry. I guess the lemniscate goes like this, would have this symmetry. The lemniscate that goes like that you saw a second ago. That has that symmetry, whatever's in the first quadrant is also in the third quadrant. Okay, so we just had to rename a few things. Sine and cosine have the first two symmetries, the last one. If we were to go look at that lemniscate, we could go see what that function looks like. But there are more than one ways to get that one. This one you do have sine, but it's a sine of 2 theta, so it's a little bit different. And you have an r squared, so you have a plus or minus. So the function is a little bit funky when you have that pole symmetry or you have that origin symmetry that we used to call it in rectangular. Let me go on back to where we were. There we go. So that's everything symmetry kind of redefined for polar curves. Let's go ahead and talk about. Oh, never mind. You guys don't have to write this because look what I put. Isn't this just saying if there's a sine, if there's a cosine, and that's all there is, which one it's going to have? Didn't we write that on the page before? Okay. So let's not worry about that. let's not worry about that. I kind of summarized it on the page before. Remember, I was trying to simplify some of these 10-8 notes. So this is good, but technically we already kind of did the quick test because we said, hey, functions with just sign will have this pi over 2, and functions with just cosine. If they have a mixture, well, who knows what it's going to be. But just sine, just cosine are going to have those types of symmetries. I want you guys in your polar mode, I want you guys to sketch these two graphs for me. Let's see what these two look like. Sadly, for the second one, what are you going to have to do to be able to put it in your graphing calculator, guys? Good. But not just positive square root, right? Remember, you have to do two different curves. So you guys are actually graphing three things. I'm in degree mode, and when I go to my window, I'm like, no, those are radian measures. We'll think I better do some degree measures, like 0 to 360 or 0 to 720. That step is going to take forever. You guys remember what the step stands for? Why do I need to change this to do this range? It's going to take forever, right? Going by 0.8 isn't it? No, we're not doing that. So let's go by maybe 5s. 5 sounds good. That's only because I'm in degree mode. Oh, that's weird. What's going on? I'm trying to distinguish. I'm making the top one bold, the bottom ones with the circles to show. My mode is simultaneous. Let's make my zoom. I'm going to go to radians. I think degrees are way too big. Since these are actually using the angle itself, I'm going to go to radians to make this much more manageable. And I'll change my windows to more radian-ish, like 6.282 pi. I'm going to go back to 0.1s. Now let's try. There we go, that's better. Yeah. Does it show up? I went back to radians because as you're plugging in thetas are always funny if it's not in a sine or a cosine. Sine or cosine restrict theta because theta, when plugged into sine or cosine, will just get between like 1 and -1. But when you just have a theta alone, it's actually going through all those numbers. So when I was going through 0 to 720, it was graphing like huge way out here with a graph with like 720. I would have needed to make my window huge. I wasn't feeling that, so I went ahead and changed to radians. That way the numbers would be small. So the values would be small. Just to make things go a little bit faster, I'll go by like 0.2s instead. As you guys notice, this one is just spiraling, right? This guy. He's just going to keep on spiraling. It's going to get bigger and bigger and bigger. So does this guy have any symmetry, the spiral? No, he is none. So there's not always symmetry. And if we zoom in, because this guy's really, really small, so if we zoom in, This one isn't really weird. You can think of this one as like the black hole. Because if you make this one, the window, if you make it go even more, like, let's go to like 20. If we zoom in even more. Guess what it's going to keep on doing? Did you guys figure it out? It's like a little vortex. It keeps on going in and in and in and in and in and in and in. I made my window keep going even more. So this was just going to keep on spiraling in and in and in and in and in. So it does kind of seem to have pole symmetry, but it is kind of hard to see. But anyway, this one's pretty nifty too. Okay, so I want to give you guys the idea between the limacons that I showed you in those special curves at the end. Those are the ones that have sines and cosines. The R curves that just have thetas are going to look funny. They're going to be different. They might not even have symmetry. All right, I want you guys to go ahead and use your unit circle knowledge to sketch this guy using strategic values. And we'll kind of hash it out. But then we're going to try and get a picture, try to figure out what it looks like. Give it a name, a limason, or a rose, or a lemniscate, or a circle, or a conic section. And then try to identify what kind of symmetry it has. Okay? Now, hold on, wait a minute. Can't we figure out the symmetry right away, what it should have? It has a cosine, and it doesn't have any sine or tangent or theta by itself. So if it just has a cosine with numbers, what kind of symmetry should I say right now? Good. Which is similar in our brains to x-axis symmetry, right? So that might help us graph a little bit faster. Can anybody think of what are some nice angles when plugged into cosine that gets out nice whole numbers or nice fractions, not the square rooty ones? Okay, 0 is good. What else? When is cosine 1/2? No, pi over 6 is square root of 3 over 2. Yeah, pi over 3. So let's try to skip the pi over 6 and pi over 4, because that would be weird square root of 3 over 2 and weird square root of 2 over 2. We're not feeling decimals. Let's see if we can figure it out without the decimals. So we're just using the 90s, the 60s, and the zeros. Let's see what else. I'll stop at pi for right now. We might need to go some more, but we'll see if we can get a good picture. If you plug in 0 to cosine, what do you guys get? Cosine of 0 is 1. 1 times 2 is 2. 2 times, or plus 3 is 5. Okay. If I plug in pi over 3, cosine of pi over 3 is 1/2, right? What's 1/2 times 2? 1. 1 plus 3 is 4. What happens when I plug in pi over 2? No, that's pi over 4. 0. Good. So that's going to be 0. This one is going to be 1/2. This one is 1. 2 times 0 is 0. 0 plus 3 is 3.
Well, that's going to be -4 then 4.
Because cosine of 2 pi over 3 is now -1/2, right?
Yeah.
That'd be 3 minus 1. That's still 2 though, right? And for pi, what's cosine of pi? -1 times 2 is -2, and 3 minus 2 is 1. Okay, let's see what's going on here. So if we start graphing, maybe we'll need to keep on graphing more points, but maybe we have enough. So do you guys see how I'm just going to do the pi over 3 line? I'm ignoring the pi over 4 and the pi over 6 because I don't need it. I'm just doing the 60 degrees. I have the zeros and 90s just for my x and y axis. How many tick marks do we need? Good. Alright, I'm gonna graph points and you guys graph points. Let's see what we come up with. I'm gonna go ahead and hide my points because I want to see if you guys can actually graph these polar points, okay? You have radians, 0, pi over 3, pi over 2, 2 pi over 3 pi. And you have values. Can you graph them? Use people in your group if you're getting a little bit stuck. Remember, we're curving around, right? Connecting the tick marks, the 4 with the 4, the 3 with the 3, etc. If we need them. You guys ready for the unveiling?
Yeah.
Okay. How'd you do? Questions? Okay. Zeroing, 0, go out. I have a 3 angle. I connected the 4 with the 4 to work in a circular fashion. Where I connected a main point. 90 degrees, go out 3. 2 pi over 3, connected 2's. Pi, and 1. Now why am I saying that you should be good to go? What can you do that? It has polar axis symmetry, so what's above is going to be below. Now, you have to kind of get used to polar curves to be able to do that. Question, could you keep on finding more points and graphing them if you needed to? Oh yeah, totally. But since I know symmetry, I'm going to go ahead and do what I did up above. Because the next point is going to be a 60 degree. It's going to copy that 2 circle, like the one above did. Then I'm going to copy the 3, like the 90 above did. Then I'm going to copy the 4 to the 4, like the 60 up above did. And then I'm going to go back. What kind of polar curve is this, guys? A limacon. Does it have an inner loop? No. It comes to a little baby, what we call a cusp. It's like a very, I don't know, distorted heart. Comes to a little baby cusp. It comes in, but it doesn't go all the way to 0. So it's not even a full cusp. It doesn't come all the way in. It kind of flattens and then goes back out. Looks like maybe the boiled egg has that flat part at the bottom. We would call this a limacon, and we already figured out that it has what kind of symmetry? How does that accent work? It's like a little,
Yeah.
like that kind of.
Yeah. Say
It's close to that. I think so.
Anyway, a limacon. It's just fun to say. Okay. Any questions on the graph? So one more time. Could you have kept going in the table? Yeah. You could have filled this in, and you would have gotten the rest of the points. But can you also use clues like symmetry and what you know about polar curves to finish it? Yes. Yes, you can. No questions. We're okay. Yeah, we need to do maximum. 2 more graphing clues. You guys can skip like 1 line. It's not going to take long. Maximums and minimums. Now, if you have something like that spiral, where there was not a trig function limiting the theta, holding the theta within, sine and cosine is a restricted function. They only go between 1 and -1. If you don't have some limiting thing around that theta can keep on growing forever and ever and ever, so there might not be a maximum. Or like that one that we saw that spiraled in on itself, there might not be a minimum. It might keep on getting closer and closer and closer, might still be coming, I guess. But if there is max and if there is a min, usually it's with sine and cosine because they're restricting. And so you can figure out, like I asked you in the last one, how many tick marks should we put? The maximum that curve would go is out to 5. The minimum, it went all the way down to 1, but it wouldn't go any lower. And here's what we think about with sine and cosine. To find the max, I'll say max or min. It kind of depends on the function as to which one's which. To find the max for min, we plug in almost always when sine, let's put it this way, and cosine equal 1 and negative 1. Because 1 is the highest sine and cosine go, and negative 1 is the lowest sine and cosine go. So if the theta is inside there, usually we'll find the max and min at the places where sine and cosine are 1 and negative 1. Which, if you plug into a table, you'll know those places, hopefully. Because you're going to use those angles, because those angles are nice ones that give you when sine and cosine is 1 and negative 1. With other functions, we'll just say right now that you can use your graph to identify the biggest the radius goes and the smallest the radius goes based on the graph, how far away from the pole and how close to the pole you go. We'll just say to use your grapher. But with sine and cosine, sine is maximized at 1, cosine is maximized at 1, sine is minimized at negative 1, cosine is minimized at negative 1, almost always. The zeros, when r is equal to 0, we're just going to say, okay, then take what r equals, which is f of theta. We can set equal to 0, we can solve with our trig knowledge. Maybe have you do some like inversely trig to try to solve. But we could set the function equal to 0 and find it, or maybe it'll just show up in our table when we're graphing. So we solve, oh, I guess you don't really need to put that second one, but you can if you want. You just set f of theta or r equal to 0, solve with your trig. Solve for theta. I basically just stated the second one. So that in homework, when they ask you to find the maximums, minimums, and the zeros, I think I have a couple examples on the next page. And let's see if we can figure it out. Sound good? You guys got it okay? I don't see pens moving. All right, here we go. So they say find the maximum of the absolute value of r. And these are taken out of directions from the section. That means what's the biggest number of tick marks? What's the farthest out? Like in the last one, you wanted to go to 5 all the way around. And we put absolute value because a positive number, it might only go positive a certain distance, but it might go negative a bigger distance, and that's the one that we would want to make the tick marks. That's the units that we would want to use. We want to use the biggest one, whether positive or negative, because that extends outward, and so we would just need to use either one, whichever one wins. So for this one, I told you guys to test when sine equals negative 1 and when sine equals positive 1. So question, kiddos, when will sine equal negative 1? Yeah, 3 pi over 2. Sine will equal negative 1. And then at pi over 2, sine will equal positive 1, right? So we're going to test 10 minus 10 times negative 1. 10 minus 10 times positive 1. So the top one, 10 times negative 1, is negative 10, but since I'm subtracting, that ends up being 20. Whereas the bottom one, that one ends up being 0. So even though the top one is when sine is negative 1, the bottom one is when sine is positive 1, the top one ends up maximizing the function. So when you make your polar graph, how many tick marks are you going to need to go out? 20 all the way around. Just go positive 20, negative 20 on the x and y axis, or on the polar axis in the pi over 2 line. So the maximum would be 20. And the nice thing is on this one, we actually already found our zero. We didn't even have to set it equal to zero. It ended up being where? Yeah. And technically we could say, and the coterminal angles with pi over 2. Because if we keep going, it's going to keep on hitting zero every coterminal angle with pi over 2. Yeah, I know. Don't worry, we can do that.
Just finding out what at 0 equal 2 pi and pi, right? Or do you want to make it 1 and then?
You could use 2 pi and pi. We could technically use something probably a little smaller, like 0 works because 3 times 0 is still 0. Because when you plug in, you would get 4 times cosine of 3 times 0. Oops, not theta, sorry, 0. Which is 4 times cosine of 0. Which is when cosine is equal to 1. Which is 4. Sean, we could totally use 2 pi, and it will not 2 pi. Because that'd be 6 pi, that'd be back at 0. We could use pi times 3 would be 3 pi, which is also going to be at the same location, but we could also use pi over 3. You know what I mean? Because when you plug into pi over 3 times 3, what do we get? There you go. And what is cosine of pi?
0.
Negative 1. Cosine is 0 at pi over 2 and 3 pi over 2. Remember? So that'd be negative 4. But yeah, we could use pi also, because that would have been an odd pi, which would have been at the same location. But either way, if we take the absolute value of each of these, no matter what, what's the maximum R? Yeah, so we only need to go out 4. Now sadly, we didn't find the zeros, so what are we going to have to do for the zeros? Good. So set R, which is the function 4 times cosine of 3 theta, equal to 0. Now how do we solve?
So we divide by 4 and take the cosine of each side of
Uh-oh. How do I get to theta? Yeah, cosine inverse, good. So I can set 3 theta equal to, asking myself the question, remember cosine inverse goes backwards. When does cosine equal 0? Oh, we just talked about that. Good. Pi over 2, 3 pi over 2. We're just trying to find like a pattern to the zeros. So I'm just trying to find a few pi over 2s. 1 pi over 2, 3 pi over 2, 5 pi over 2. I need to solve for theta though, so what am I going to do? Divide everything by 3. So instead of pi over 2, it's actually going to happen at pi over 6, because if I plug pi over 6 into my argument, it's going to be multiplied by 3. Pi over 6 times 3 is pi over 2, so it will become the angle I need it to be. The next one, 3 pi over 6, of course, can reduce 5 pi over 6. Oh my goodness, it's going to be every single pi over 6 angle and every single pi over 2 angle.
Yeah, I don't get what you did after you put the cosine inverse.
I ask myself, when in the unit circle is cosine 0? And cosine is going to equal 0 at all of the 90s. So at pi over 2, at 3 pi over 2, and I could keep on going and say not just at pi over 2, but 3 pi over 2.
That's for 3 phase, so you divide it
by
by 3.
See what I mean? I could keep on going. It's going to keep on hitting those two locations.
But those are the 3 phases.
Those are the 3
divided by
thetas.
3.
So I had to solve by dividing both sides by 3.
So all the pi over 6 is.
Yeah. Well, true, but 3 pi over 6 reduces to a pi over 2. So you get the pi over 2s and the pi over 6s. Yeah. So then my zeros are going to be, you could just say, to make it simplistic without going into like coterminal notation, you could just put B when x equals all the pi over 6 angles and the pi over 2 angles. So 1 pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6, and pi over 2, 3 pi over 2. If you were to keep going, it would keep on hitting 0. Okay? So that's maximums and zeros, a little bit funny, still uses unit circle knowledge, uses knowledge that we've done in the past, solving trig equations, etc. So let me have you guys try one more. Once again, I'm just asking you to sketch. From the sketch, you can tell me usually the zeros, the maximums, the minimums, the symmetry. Let's see if by sketching you're able to find each of the different characteristics that I'll ask for. I know we're getting close, but question, what kind of symmetry do we have?
Polar axis?
Good, and you guys could look that up if you needed to, right? Which one does cosine have? Since it's cosine, what kinds of nice angles are we going to use again? Nope, pi over 6s would be nice with sine. Pi over 3s are nice with cosine. Pi over 6s would be nice with sine. What are we going to try to do after we find each of the points? See if we can figure out the graph. Kiddos, we basically got to the end of 10.8 because now it's just the special pictures. So let's see what you guys can do with homework. Maximums and minimums, you can try to use the solving, or you can just make a graph and see if you can find it. Alright guys, we'll check all the homework tomorrow and go over questions.